No, it's fine. So if you were at the TI of our entrance interview and and there were 5 people looking gravely at you and saying, "What can you say about this problem?" What you would probably do is to plot this potential. So let's just do that. Okay. Let's see what we can say about this problem. Okay. The first thing we're going to do is look at large R. Centrifugal potential, right. Shall I get rid of this 1 from here?
1 can be
absorbed into that. Let me get -1. Excellent. So the first thing I do is I look at this potential and I see that far away, which term dominates? -1 by minus what was beta by? Minus beta by r, yeah. The mass. Very, very Newtonian, right? Okay. So this is always true. Now, as we move nearer and nearer in, let's look at r equals 0. Okay? At r equals 0, what dominates?
R1 by r cube.
-1 by r cube. Okay. So let's give ourselves a little more space. Okay, this E tilde, anyway, yeah. Let's give ourselves a little more space here. So at near 0, this is -1 by r cube. It's going down pretty fast. Here it's -1 by r. Okay. Now, when this happens, there are 2 reasonable possibilities. One is that you just join it up. The second is that there's some maximum and a minimum. Okay, let's see how it goes. In order to judge whether there's a maximum or minimum, what we'll do is take this and differentiate it. Let's use 1 over r as our variable, so we don't have to, so we can deal with polynomials rather. Okay, so let's call 1 over. Let's say x is 1 by r. So this thing was L tilde squared x squared minus beta x cube minus beta x. Okay. So let's differentiate this. So when we differentiate it, we get L tilde squared into 2x minus 3 beta x squared minus beta is equal to 0.
So the relative value of L square and beta would dictate what form the potential is.
Exactly. Beta is just the mass, of course. L is, how fast it's moving. Okay, so fine. Now, let's see about the important question is when this thing has solutions. Okay, so the equation is written out better is x square 3 beta x square minus 2x plus beta by L tilde squared is equal to 0. Right? Now, the key question is what is the sign of b squared minus 4ac? So b squared minus 4ac is 4 minus 12 beta squared by L tilde squared. Four minus 12 beta squared by L tilde squared. Okay, so now depending on whether okay, so there are two cases. The first case is 3 beta squared is greater than L tilde squared. In this case, no max. No extrema in the middle. Okay, so in this case, in case 1, let's call it. Okay, this function will look like this. On the other hand, in the other case is the reverse, which is 3 beta squared is less than L tilde squared. Okay, 3 beta squared is less than L tilde squared. Then there are two local extrema. So clearly, in that case, what we will have is something that looks like this. This will rise, it will come down and then go, something like that. I'm not totally sure I want to indicate that these two things cross each other. Let me not draw them in the same graph. Okay, so this is one case, and the other one is a monotonic thing. Can it ever go above E is equal to 0? Probably not. Let me think about that just a minute. Let's see. What is the magnitude of this? The magnitude of this is this quantity. Now, this quantity here was the energy in units of m. No, so it can. You see, this is the question. That's on this side. Yeah. Wait. So this potential is the. It would be the see. So when this thing was 0, that would be, the situation where you let a particle go from infinity, because then the energy would be exactly equal to the rest mass. Okay, and if it ever went above, it would be a situation where yeah. So I think it can if L is large enough.
It's like a hyperbolic path.
Exactly. It's some path where you've got so much angular momentum that it can never come. It can never go in. Yes, I think it might. It could do that. Okay, excellent. Now, the important thing about this potential, one important thing about this potential is these two extrema. When these extrema exist, okay, they represent, what do they represent?
Stable and unstable circular orbits.
Circular orbits. Okay, they represent circular orbits because at the extrema, R sits there and is not evolving in time. And that's the definition of a circular orbit. Okay, so if you're sitting here, as you said, we've got a nice stable circular orbit. If you're sitting here, we've got an unstable circular orbit. Okay, If you're a little bit perturbed away from the stable circular orbit, you'll oscillate around here. That'll be the analog of a stable elliptical orbit. Okay? If you have a little unstable whoosh around here, well, if you go this way, bye-bye. Okay, good. So now you have the formalism in hand, and I can't remember if I gave you the assignment, but now I'm going to give you the assignment. The assignment is using all of this, show that there are no stable circular orbits with (3m). So that's, I suppose, beta by 2. 3. Okay, I'll give you a couple of problems with the problem set where you sort of explore the phenomenology of these orbits. So you just understand what motion in this Schwarzschild black hole background will be. Okay? For the purposes of the class, we've set up the problem. Now you need to explore. And I'll give you a couple of problems in the problem set to help you doing the exploring. Any questions or comments? Otherwise, we'll move on. You see, by the way, how nice this effective potential kind of thing is. How much nicer it is than working in terms of the crude, non-covariant way. It's all the same information. It's all the same information, but it's so much more transparent. And the key point here was that we had a formalism that allowed us to treat tau as an independent parameter. So we could think of motion in tau in some clean conceptual way. Okay? So, okay, one other exercise we'll do. Exercise, how does this change when we consider massless motion? What changes when we consider massless? Reformulate this problem. Exercise. If you have, we have the following situation. You've got the Earth, you've got the Sun. Oh. So we've got the Sun, the Earth, and a star. Okay, such that the light from the star is coming towards the Earth, just grazing past the Sun. Okay, the Earth is here, let's say. Okay, so in the absence of the Sun, this was the configuration. In the presence of the Sun, this light ray bends a little bit, so that what we actually see is something like this. There's a bending in the angle theta. Okay, in terms of the mass of the Sun and the radius of the Sun, compute theta. Everything's small, so you can use small approximations. For this, you would have to use your reformulation for massless motion. By the way, if you wanted actually, from this problem, if you wanted a complete solving for the motion, can you tell me what algorithm would you follow? Suppose I wanted to find the full orbit, corresponding to some L and some E. I wanted to find an orbit. Let's say, for instance, that the E put be here. What would you do? Well, the first thing you would do is solve for the motion of r as a function of tau. You'd have to do an integral to do that. It's the usual thing. Once you have r as a function of tau, you plug into the formula for the conserved angular momentum. You'll get phi as a function of tau.
And then eliminate tau.
Yes, then you plug into the formula for the conserved energy. You'll get t as a function of tau. Okay, and now this is a parametric representation of your orbit because you've got t, phi and r as a function of something. That tau happens to be proper time, but you need not worry about that. So you can eliminate tau in favor, for instance, of t. Okay, and that will give you phi as a function of t and r as a function of t. Okay, great. Fine. Let's proceed. Let's proceed. Any questions or comments about this? Okay, you'll explore. You'll get more intuition for what happens in your problem sets. We'll have 2 or 3 problems designed to give you intuition for what happens. Okay, that you'll do when you.
This scenario should reduce down to Newtonian gravity if theta goes to 0, right?
Yes. Okay, let's see approximately where that's coming from. You're going to have to help me write that equation again. Can you?
So e to the squared equals dr by d tau squared.
Could we have the final equation with e tilde minus 1? It was dr by d tau squared
L tilde squared by r squared
plus m tilde
L
L tilde squared by r squared
and
into
1 minus beta
by r
It comes from the numerator.
1 minus beta by r
And then minus beta by r.
minus beta by r is equal to e tilde squared minus 1
Squared, e tilde squared.
e tilde squared minus 1. Okay, firstly, if we're interested in Newtonian mechanics, this thing is already order epsilon. Remember our counting? All kinetic energies were order epsilon. Potential energies were also order epsilon. Okay? So if I count this as order epsilon, this will already be order epsilon. And so the correction between dr by d tau and dr by dt, which itself is a fractional correction of order epsilon, because, do you understand what I'm saying? Okay, let's say we were in flat space. Okay, what is tau? Tau is equal to t, and we're moving with velocity beta. 1 minus beta squared. But this guy is order epsilon. So tau is equal to t plus correction order epsilon. But this was already order epsilon, so the correction we can ignore. We're going. So this thing here is dr by dt, the whole thing squared. Okay. Now L is m velocity square. Also order epsilon. It's r square velocity square. So this is r square by r square m order epsilon. We can ignore this. Okay. So plus L tilde by r squared. This is order epsilon. We can't ignore it. It's there. Minus beta by r. What about this quantity? What was E tilde? E tilde, you see, let's now write it in terms of relativistic energies. Okay? E tilde was the full energy divided by m. But the full energy is m square. The full energy is m plus kinetic energy, extra energy. Oh, let's write it as binding energy, minus delta EB. E is equal to this. Okay? E tilde was this divided by, so it's 1 minus EB by m. Okay? I now expand this, the 1 cancels, and I'll get 2 EB by m. Okay? I'll take the m by 2 to the other side. So we get m by 2 is equal to delta E, the minus. Okay, and this is good old Newtonian Lagrange. Clear? By the way, having a circular orbit gives you a relationship that tells you what the energy is in terms of your angular momentum. Beta was the mass of the sun. That is some fixed thing. It's the mass of the thing that's causing the potential. In our head, let's not vary beta. For particle motion, what we can vary is E and L. Okay? So we've got this fixed thing here, and we've got some E. As we've seen here, if we want some bound motion, this E tilde minus 1 will be some negative quantity. If we want unbound motion, E tilde minus 1 will be up here. Okay? I was going to give you problem sets and all this, but let me just say some of this. Okay, so E tilde minus m will be here, let's say, for bound motion. So where you are here in E tilde determines your orbit. So tup. Okay, yeah, given your L. Okay, if you have a circular orbit, E tilde is determined in terms of L. That's intuitive, right? For circular orbits, there's not much. The only play is how far you are.
Yeah, dr dt goes to 0.
Dr dt goes to 0, so you have to be either here or here. So on circular orbits, you don't have a 2-parameter set of orbits, you have a 1-parameter set of orbits. So if I tell you what E is, I tell you what M is, I tell you what L is. Okay? For non-circular orbits, you have a 2-parameter set of orbits. This is basically, what is this? It's basically your eccentricity of the orbit. How much your major axis differs from your minor axis to the extent that the thing is elliptical. It's not elliptical anymore. But to the extent that it's elliptical, it's the difference between how far you go and how near you come. Why is it not elliptical, by the way? This looks like beautiful periodic motion.
Because it's not a central, one of our Kepler potential.
That's right, but what in our algebra will make this not be periodic motion?
It's not symmetric about the
Symmetry has nothing to do with periodicity. There will be some time period over which this will keep going.
It's not, since the force is not r squared, it's not a closed orbit.
Yes, can you say that in terms of our algebra? Here it looks pretty close to me. All that you guys are saying from knowledge. I want you to say it from logic. Here it look, I'm asking it's a straw question. It's a what I'm saying stupid, but I want to hear you tell me what's stupid. My stupid statement is that look, I see a nice harmonic oscillation looks very periodic to me.
But we don't get the trajectory in time. We see only the bounds of the orbit.
Yes, and so
from this we can only say that the orbit is bounded between R1 and R2.
okay, excellent. That's correct. And how would you figure out now whether this thing was something like a closed orbit or not? Yeah, exactly.
Radial frequency.
Exactly.
Angular frequency.
You calculate this motion and then check in one zoom how much have you gone in phi. If you've gone 2 pi, you're good. That's what happens for Newton. If you've gone pi or 3 pi or some rational multiple of pi, you'll also have some closed orbit. And in general, you go some irrational multiple of pi, it means you've got no closed orbits. That's how you will see the deviation from the ellipticity in this way. You will see how much, what you would do is to look at one of these things. You'd go around, calculate the r as a function of tau, plug that into phi as a function of tau, and integrate over the whole one cycle and see how much phi deviates from 2 pi. That's how you would calculate the ellipticity of the orbit. Okay? Any intuitive questions that you have about these orbits, we can address. Otherwise, we'll go on.
So can this be put in the Hamilton-Jacobite form and
It can. It's in fact, that is in some way the most beautiful way to solve the problem. It's because the Hamilton-Jacobi equations del s by del this del s. If the Hamilton-Jacobi equation is essentially, in this context, g mu nu del s by del x mu x nu 0. And this breaks up into an r derivative, del r squared, del t squared, del phi squared. And then you find solutions of the form function of phi plus function of t plus, solve it in the usual way. It's very nice because it's very covariant. Okay, that can also be done. It's not really needed, but yes, it can be done. In fact, if you look at how Landau-Lifshitz solves for these orbits, he uses Hamilton. Okay, if you'd like to look that up, go ahead. I won't spend time on it here, but it's completely equivalent. Okay, any other questions or comments? Okay. Right. Okay. So let's move on. What I wanted to do now was to return to the study of global structures of space-time, just for maybe 30 minutes, explain to you a little better this business about Penrose diagrams, about structures of space-time, and explain to you a little better the structure of the space-time of a Schwarzschild black hole when you don't stay far outside the horizon. Okay? So as a first exercise, let me tell you better what I was trying to say about, I've drawn for you a Penrose, what we call a Penrose diagram of flat space. I want to explain in equations what that diagram means. Okay? So let me do that. Let me start with the metric of flat space, which I'll write in polar coordinates. So ds squared is equal to minus dt squared plus dr squared plus r squared d omega 2 squared. Omega 2 is the volume, the line element on a unit 2 sphere. Its detailed form will play no role in anything. Okay. Then the next thing I do is define two new coordinates. I'll define a coordinate u, which is t minus r, and a coordinate v, which is t plus r. And I can't swear that other people don't define it the other way. Okay, it's one or the other. Okay. Now, the next question I have is, what does the metric look like in these coordinates? Now, the reason I define t minus r and t plus r, this is flat space Eddington-Finkelstein kind of code. It's exactly right. It would be Eddington-Finkelstein if we went to u and r. But what I'm going to do is now sort of the analog of a Kruskal coordinate, because I'll go to both u and v. Okay, I'll just work in this uv coordinate system. So you see, what we get, du dv is clearly dt squared minus dr squared. So the metric is ds squared is equal to minus du dv plus r squared d omega 2 squared. Is this clear?
shouldn't we write the r square as u v minus u?
We should, absolutely right. So let's do that. So the comment here was that this is not a very consistent way of writing it, because there should be no reference to anything but the coordinates that you used for your metric, and that's absolutely right. So r is v minus u by 2. So we'll write ds squared is equal to minus du dv plus v minus u by 2 squared d omega squared. Now, before proceeding, let's clarify the range of coordinates. Okay? R went from 0 to infinity. T went from minus infinity to infinity. So as I scan over this range of coordinates, what happens to u and v? Minus infinity, but with the constraint that v minus u is greater than 0. Because v minus u is r. Okay? Subject to this constraint, our coordinates run over all values.
The half plane.
Exactly. So if you had a VU space, we draw the line V is equal to U, and it would be above that. Okay, good. Okay, good. Now, the next thing I do, okay, the next thing I do is to write V is equal to tan V, and U is equal to tan U. Was it the other way? Yeah, this is right. Sorry. Oh, U. No, ordinary tan. I want an ordinary tan because I want something that will range over all allowed values. Hyperbolic tan only ranges from 0 to 1, but this u and v range from minus infinity to infinity. So hyperbolic tan wouldn't be very good. Okay? Now let me plug this in here and see what I get. Okay, so the derivative of tan is sec square, 1 by cos square. Okay, so I get ds squared is equal to minus du dv divided by cos square u cos square v plus tan u minus tan v minus tan u, or tan v sin u by cos u minus sin v by cos v, the whole thing squared d omega 2 squared. What? Multiplied by 1/4. By 1/4. Thank you. Correct. Now you say that this is ds squared is equal to 1 by cos square u cos squared v into minus d u dv plus 1 by 4 sine of u minus v square. Okay. Now, what was the point of all these manipulations? You might think that it's a very strange thing to do, to take beautiful, lovely Minkowski coordinates in flat space and to maul the space into looking like this complicated thing. And it is a strange thing to do for most purposes. You wouldn't dream of solving a minimally coupled scalar equation in these variables. It would be a masochistic thing to do. However, what we have done here is the following. What we have done here is to compactify space-time. What does that mean? As T and R ran from minus infinity to infinity and 0 to infinity, our little u and little v coordinates continue to run over an infinite range with this one constraint, but okay. However, you see the reason we chose this tan here is that capital V and capital U run over a finite range for its tan to run over an infinite range. Okay?
Is there a reason why we went to U and then use the tan? Like
We could have done it directly. It's just that I want to show you step by step. I wouldn't remember it like that. Okay. Yeah, see, this was a very natural thing to do. The UV was a very natural thing to do. Okay, there's a more serious sense. It is that clearly U and V were coordinates adapted to light rays. U is equal to constant is the motion of a light ray. An ingoing or an outgoing light ray at a fixed angle. So I first went to coordinates which are very naturally adapted to light rays in a sort of affine parameterization. It's like going to, it was a very natural thing to do. That first set of coordinates that are UV would also sometimes be useful for dynamics. You would sometimes find it useful to actually use it, solve a minimally coupled scalar equation in those coordinates. That's somehow a very natural thing. And then from there we did what, just, yeah, okay, sorry, just, okay. Okay, now let us more carefully examine what happens to U and V at the various boundaries of our space.
Capital U and V is in the principal values of the inverse, right? Because tan inverse.
Excellent.
Minus pi by 2 to pi by 2.
Okay, so Shubhajit's asking, where do U and V lie? So as he suggested, it's a matter of definition, but we will choose U to lie in minus pi by 2 to pi by 2. And V also to lie in minus pi by 2 to pi by 2. We don't need to choose more because tan repeats with the periodicity of pi. So we can get all values of little u and little v by choosing this. This is our choice.
And one more thing, it's a compactification, but it's a conformal compactification.
It's a conformal compactification. Exactly. See, the coordinate range is finite, but of course distances remain infinite. Why? Because the edges, what are the edges of tan? At plus minus pi by 2. At those places, cos goes to 0. And we've got a factor of 1 by cos square u, 1 by cos square v out here. So at the edges of our coordinates, that's, a lot of space is fitting into pi by 2 or minus pi by 2. We're seeing that from seeing that there's a huge amount of distance there. Is this clear? Okay? So all of this is being hidden in this distance factor. But it's an overall factor, which for many purposes is very useful. We'll discuss that.
Conformal compactification in the sense of angle preservation?
Conformal compactification in the following sense, that the metric is some overall function times some other metric. Okay? So suppose I look at this thing here and write ds tilde squared is equal to minus du dv plus 1 by 4 sine squared u minus v d omega 2 squared. This is a new metric. It's not flat space. However, this metric is related to flat space by being an overall function times flat space. Now, if you wrote down the geodesic equation in this metric, you get a different equation from the geodesic equation in this metric in general. You wrote down a minimum, you've solved Maxwell's equations. Actually, not Maxwell's equations are conformally embedded. If you solved a massive scalar equation in that metric, you'd get a different answer from this metric. Okay, but there is one thing here that is the same, and that is the causal relations between points here and points here. Because you see, the question of whether two points are time-like, light-like, or space-like separated infinitesimally is preserved by multiplying by an overall factor, because it's just a question of signs of ds square. And signs are not changing.
As long as the overall
As long as the overall factor
factor is positive.
is positive, which it is here.
And this will also preserve angles.
Will also preserve angles. Absolutely right. Absolutely right. It will preserve angles. It will preserve spatial angles, space-time angles. Absolutely right. But the thing that is of real importance to us is the causal relation. In fact, causal relations is a preservation of a particular angle, because it's a 45 degree between time and space. That's important. Okay? So if you want only to understand the causal relations between all the points in your space-time, you can as well use these, work it out in this metric as in this metric. Okay? And the advantage of the second metric is that because the advantage of the second metric is that because this coordinate is compact, you can draw it on a sheet of paper, including infinity. Okay, and we'll see that at work. So now let's see this. Now that we've got this, you might want to undo this funny UV business. So somebody has to help me. How did I define U? Was it T plus R or T minus R? So now I'll define U is equal to T minus R. Okay? And V is equal to T plus R. Okay? And so we get ds tilde, the whole thing squared, is equal to minus dt squared plus dr squared plus sine squared. Now v minus u, or u minus v, it makes no difference actually because it's squared, is 2r squared, 2r. So sine squared 2r by 4 b omega 2 squared. Okay, and now the complicated thing that's left is to figure out what are the ranges of all coordinates. So that's what we have to do slowly and patiently. But before we do that, let's look at this metric. It's a quite interesting metric. You see, this is very much like the metric of flat space. Minus dt square plus dr square, the only way it differs is that spheres at each point, instead of growing, instead of their size behaving like r squared, they grow at a different rate. And in particular, we will see that this, in particular, they never become arbitrarily big, because sine is a bounded function. So near r equals 0, they start growing and then they decide to saturate out. And at infinity, at large r, this thing becomes like the direct product of 3 directions, a time direction, an r direction, and a sphere. Okay. Of course, well, we see this a little bit. Okay, so if you go to r large enough, that sphere becomes fixed size. Okay, but now before we start really trying to interpret this thing, we have to understand all the coordinate ranges. So let's go one by one. Let's go through our coordinate transformations and slowly work out all ranges. So we already had the ranges here. U and v both went from minus infinity to infinity, but with u minus v, or v minus u greater than 0. Now, let us remember that tan in the range that Shubhajit advised us to use, tan is a monotonic function. Okay, so if little v is greater than little u, that means capital V is greater than capital U. Okay, both these wanted to range from minus infinity to infinity, which means both capital U and capital V will range from minus pi by 2 to pi by 2. So we had u and v both lying between minus pi by 2 and pi by 2, but v minus u is greater than 0. And now finally, we'll move to these t and r coordinates. Okay, so now we have to understand what this means. We have to understand what this means in terms of ranges. Let's immediately draw this in a diagram first. Let's immediately draw this in a diagram first, though, before we do that. You see, what we will, because u and v, lines of constant u and lines of constant v are lines of are light rays. Why was that the case? At fixed angle. Why was that the case? Because lines of constant little u and lines of constant little v were fixed light rays, and if little u is being held fixed, so is capital U, because capital U is a function only of little u. Okay, so because of that, when we draw these coordinates, we will draw these lines as 45-degree lines. Okay, so let us draw a sort of axis like this, where we have lines of constant. Now, which one? Just a minute.
So is this TR plane?
No, at the moment I'm drawing the UV. Well, it will in the end be the TR plane, because I'm going to draw this at 45 degrees. Okay. So I'm going to draw u, which is t minus r. So as I increase t, I increase r. So my lines of constant t, so constant u are these. These are lines of constant u. So the u axis goes this way. I mean, if this is u equals, if this is u is, so this will be u equals, this whole line is u is equal to minus pi by 2. And this whole line is u is equal to plus pi by 2. Or however you say that. Yeah, okay. Okay, then we've got the lines of constant. We've got lines of constant v. They go the other way. Okay, v also increases in time. Okay, so and I need I'm going to clear some of this. Is that okay? So let's draw let's draw a diamond. Let's start by drawing a diamond. Okay? So our lines of constant u went this way. There was same range for u and v, apart from the inequality that we have to ensure. These were lines of constant u. these were lines of constant v. And here we will label what they were. So this was minus pi by 2, and this was pi by 2. So that they increase upwards. So t is roughly that way. Okay? Similarly, okay, so this quantity here is minus pi by 2. This quantity up here is pi by 2. So this would be the whole UV plane in this diagram, apart from the inequality. Now what is the inequality? The inequality is V greater than U. V greater than U. Yeah, so now where is that on this line? Let us see. It's the right half, yes. Because this is the line V is equal to U. At this point, V and U are both pi by 2, minus pi by 2. This point, V and U are both pi by 2. And you see, there you go, that this is the line V is equal to U. V is greater than U in the right half. Okay, so this whole conformal compactification here is this with this removed. Shall I remove it? Such a nice diagram. This quantity is called the Penrose diagram of flat space. What it depicts most clearly, see, this diagram, this metric here captures all causal relations. This diagram sacrifices angle information, which means that it's a faithful representation of causal relations at a fixed angle. Okay? If you want a faithful representation of causal relations, including angles, you need to draw a 4-dimensional diagram. You can be my guest. Okay? Okay? But it gives you a sense of what. If you want to think of this, in some sense, what you should think is that each point here represents a whole sphere. But these lines are lines at fixed angle. Okay? They represent the motion of light rays at fixed angle. Is this clear? Note that blue light rays are ingoing light rays. They come from infinity and go in. Note that white light rays are outgoing light rays. They emerge from an interior point and go out to infinity. Okay? Notice that these things here are very far away. You say, what are we doing to be at a point here? We're taking r to infinity, but t to infinity, such that r minus t is held fixed. Because that's the definition. This point is along one of these lines. These lines were constant u, and u was t minus r. Okay? What are we doing to come along here? We're taking r to infinity and t to minus infinity, so that t plus r is held fixed. This is what a light ray that comes from infinity does. This is what a light ray that goes to infinity does. What does this point have in common with both these things? R going to infinity. This point is never reached by any light ray except, well, this extreme light. Okay? You should think of it as never reached by any light ray. Okay? And this point represents spatial infinity, taking r to infinity at fixed time. Okay? All of r to infinity at fixed time is one point on this diagram. Okay? Whereas this diagram likes light rays. So a torch that's put on now and a torch that's put on a few minutes from now reaches a completely different point on the boundary of this conformal compactification.
There's no two-sphere at that point, at the spatial instant.
Well,
I mean, the factor with the two-sphere goes to 0.
the factor with the two-sphere goes to
Psi square u minus v.
That's in the conformal.
no, it's u is equal to v is this line.
Oh, yeah, sorry.
Okay, this is where this factor goes to. This thing, this will actually go to 1/4. It's like capital R going to infinity. I mean, sorry, capital R going to, it'll be,
Pi.
yeah,
Pi 2.
yeah, it'll be some fixed number, but let's figure out what that number is. This thing here is the limit. It's a bit
Yes, sine square pi. Yeah, that's 0.
it's a bit
Sine square pi.
yeah, right, you're right, yeah, you're right. Because here, this guy is minus pi by 2, whereas this guy is pi by 2. So, did I really do that right? Sine square pi, that's 0, right?
Whole R line is the center of the coordinates.
What?
The whole line.
Uh-huh.
Oh, okay. This coordinate is R coordinate.
This coordinate is, yeah. But the question is, what value of r do we reach? Because this could go to 0 if this reached pi, or pi by 2, right? Capital R equals pi by 2, and maybe that's maybe you are right. Just a minute. Just a minute. From here, if I've got these factors of 2 right, this is unambiguous.
Yes.
Because this is pi by 2. It's pi. I think you're right that if
And R is also pi by 2 over there in that coordinate.
in that coordinate. That probably is right. Yeah. Yeah, because you are minus of each other. So in that line, this capital T is 0, which is correct. R is pi by 2 if u and v are both pi by 2. I think this is right. I think you're right. I think you're right that R is that this thing is going.
What does that mean that in the
Yeah, what does this mean? It's a good point. Let's look at how the size of the sphere varies as we move along along this.
So there is a 1 by cos square u cos square beta, and in between 1 will cancel this 0.
No, of course, this sphere doesn't really go to 0.
yeah, I mean,
But it goes to 0 in the conformal compactification.
Okay.
So he's asking about conformally it goes to 0. Yeah. This is a good question. You know, let me tell you what. Okay, let me tell you something I was avoiding telling you about this space, which may help clarify this. Let's look at this whole. Yeah, let's look at this whole metric here.
three-sphere.
It's the metric of a 3-sphere. Okay, it's the metric of a 3-sphere once you identify this guy here as an angle. Okay, so what we're getting here is, so 3-sphere divided by 4, I believe.
4 is taken care by the R.
You move to the coordinate 2r.
Yes.
Exactly. So you move to the appropriate coordinate. Exactly right. So then we'll get 1 by 4 times d r prime squared plus sine squared r prime squared times. Now this is a 2-sphere. This is a 3-sphere. In this 3-sphere, we've got this angular coordinate. You know, the 3-sphere, just like a 2-sphere, can be thought of as a circle fibered over a line, which is a fancy way of saying a 2-sphere is a bunch of 5 circles whose size depends on where you are in theta. There are 2 points where the 5 circles go to 0, flares out, comes back. So 2-sphere is, mathematicians like to say that this 2 spheres, a circle fibered over a line, and it's non-trivial fibration because this goes to 0 at some point. In similar way, a 3-sphere is a 2-sphere fibered over a line, and at 2 points the 2-sphere goes to 0. Okay, so in this 2r coordinate, that would happen at let's say r is equal to 0 and 2r is equal to 0 and 2r is equal to pi. Okay, and so we're hitting one of these points. Nothing particularly bad is happening in the whole space, because the whole thing was just a 3-sphere. It's like a coordinate singularity. Okay, however, it is striking that there was something special of the actual 2-sphere that was going to 0. This probably has some meaning. I don't know. I don't have anything good to say about it for now. It's quite striking. Notice that the size of this thing will vary as we move along here, because as we vary, we'll change. We'll change the one of the two stays fixed. Let's say we're here. That is v, I suppose, staying at pi by 2, but u changing. So then the size will vary. Probably come to a maximum somewhere in the middle. Okay, we could figure that out. That's not going to be important for what I wanted to say, but it's an interesting question. This metric, by the way, is sometimes called the Einstein static universe. It's a universe in which you've got a three sphere in space times time, and it's called the Einstein static universe because Einstein suggested at some point that the equations of cosmology might have such a solution. Something we will discuss.
So the topology is S1 cross S3. Yeah.
It's time cross S3. Time is time-like, so it's different.
So this one is.
Yeah. Okay. Of course, the actual topology is mauled a little bit by the fact that not all of the r coordinate exists. So it's some part of this 3 sphere times time. Okay. Fine. But let's get back to the. No, it doesn't satisfy Einstein's equations. But it does satisfy Einstein's equations with the cosmological constant.
Oh,
okay. And if you tune things, you know, Einstein, when he wrote down his equations, wasn't prepared for their consequences. No, but yeah, it's such a tremendously. So one of the consequences of his equation was that if you didn't have a cosmological constant, a static universe, and you had matter, a static universe is impossible. But Einstein knew, like everyone at his time, knew that the universe was obviously static. It's unchanging, it's been there forever. So he thought it was a blow against his equations that it didn't allow for a static universe. So he changed the equations to get a cosmological constant, fiddled about with the signs so he could find it static. But it's an amazing thing about that guy that, okay, so firstly he was able to do this. Then Hubble discovered that the universe was expanding. And, you know, Einstein thought this is ridiculous. You know, I had a chance to make a prediction of a lifetime. And I gave it up for some tinkering with my equation. And he said, he called it his greatest blunder, famously in print. He said, this was my greatest blunder. Yet, fast forward 85 years from now, looks like there is a cosmological constant. It's non-zero. It didn't make the universe static. But it exists, you know, so if you're making blunders like that one, you're doing well. Yeah. Okay, we'll come to this. When we discuss cosmology, we'll discuss these things as solutions to equations of motion. Okay, but for now, forget about it. Forget about this. What I want you to focus on are the causal relations. This is a causal map of flat space and shows you that for causal purposes, different light rays are very different, even when they go to very large times, very large distances. Whereas all points at spatial infinity and all points that go to t equals infinity at fixed r, or t equals minus infinity at fixed r, are essentially the same for causal purposes. Okay? So these pictures, this flat space is very simple, but already it's useful to keep this diagram in mind when you're discussing scattering in a theory with massless particles, for instance. because the particles come from here, they go here. Causality tells you that if a particle comes from here, it should never be able to affect anything here before this ray. So it's already, it gives you interesting ways of thinking of flat space when thought right for causal purposes. Okay, but okay, flat space is very familiar, it's not very complicated, and fine. This was all that we did with these conformal diagrams. These are sometimes called conformal diagrams, conformal compactifications of space-time. Would not be that much. I'm now going to describe the analogous thing you can do for black hole geometries, which is much more surprising and much more interesting. Okay, so now let us go back and look at the Schwarzschild metric. Let's go back and look at the Schwarzschild metric. We had written it in Schwarzschild coordinates, ds squared was equal to minus dt squared 1 minus beta by r plus dr squared over 1 minus beta by r plus r squared d omega 2 squared. In what I'm going to be doing now, this will play as little role as it did for the flat space. So I'll sometimes not even write it. Okay, it's there, but it's playing no role. Okay. Now, you remember we had already discussed these Eddington-Finkelstein coordinates. These Eddington-Finkelstein coordinates were what? We discussed a coordinate v, which was t minus integral dr divided by 1 minus beta by r. Was and u, help me get the signs right. When we were doing this thing, was v t minus r or t plus r? Okay. Just to be very concrete, I'll work out the integrals. We've done this once before, but let's do it again. Okay, v was equal to t plus, now what did we do is we said this was r minus beta plus beta plus r minus beta log plus beta log r minus beta by beta. Well, that's a choice of integration constant, and u is equal to t minus r minus beta log r minus beta by beta. Okay, so we've got the v coordinates, the u coordinates, these u coordinates. Now, what we did last time was to move to coordinates that were either v and r or u and r. Okay? First thing I'm going to do is to ask, what do v and r look like in terms of the Penrose diagram when we go to large R? There, we can forget about all this stuff. So v and u just become the v and u we've been talking about before. So what are lines of, the Penrose diagram might get modified as we go towards r equals beta. In fact, it will. But large R it can't because it's the same space. So this Penrose diagram will certainly have, all this is large R. So it will certainly have this business. Okay? What were lines of constant u? Well, as r increases, t increases, those were these. What were lines of constant v? Right? As r increases, t decreases when v is constant. Yeah, I'll draw these in blue. Okay. Now we saw, if you remember, that there was a particular value of r, okay, at which we hit the at which r was equal to beta. Now let's look at this thing. Notice that r is equal. So let's suppose we were drawing. We were working with Eddington-Finkelstein coordinates. In the coordinates, let's write it down once and for all. V. This is r. This is r increases, t decreases. So that is V. V is blue. Okay, so suppose we were working in Eddington-Finkelstein coordinates in V and R. At some r we encounter r is equal to beta. We encounter that at various different values of V. So let me write down the metric also, just so that you have that in front of you. We have ds squared is equal to 2 dv dr, okay, plus minus 1 minus beta by r dv squared plus r squared d omega 2 squared. Okay. Okay, so we've got ds squared is equal to 2 dv blah blah blah. We, at various different values of v, we encounter the surface r is equal to beta. So these lines, these v is equal to constant lines, must be hitting the surface r is equal to beta somewhere. But what is this r is equal to beta surface? R is equal to beta surface is a line of constant r. Okay, it's a line along which v is varying. But if r is constant and equal to beta, this term is not there. So if r is constant and v is varying, ds squared is 0. So this line r is equal to beta is a null line. It's a null line that is meeting many v lines. Where can it be? It has to be some null line like this.
Some constant t.
Some line like 40, all null lines are 45 degrees in this plane. It can't be 45 degrees this way because then it wouldn't meet many lines of constant v. So you see the line r is equal to beta. In this diagram must be a line like this. But exactly the converse is true in the other Eddington-Finkelstein coordinates. R is equal to beta in the Eddington-Finkelstein coordinates with u and r. Okay, must be a line that meets many constant v lines. So it must be a line like this. If there are two 45-degree lines, they must meet somewhere, so there's some point where this meets. But we can say more. Because you see, r is equal to beta as that was the whole point of these Eddington-Finkelstein coordinates. R is equal to beta was not a particularly special place in our diagram. We could go through. So these lines could be continued until they went to r is equal to 0. Right? These were lines of constant v, and they went all the way until they met a particular r. This r is equal to 0 is a line like this. We'll calculate the angle in a bit. It's just flat. Okay, we'll calculate why I'm drawing it flat. Some end of the diagram. This is a genuine end of the diagram because there you hit a singularity. You can't go beyond that. This is a curvature singularity. It's not some coordinate thing. Okay? Similarly, r is equal to 0 here goes like this. Do you see that in this conformal compactification, r less than beta in outgoing Eddington-Finkelstein and r less than beta in ingoing Eddington-Finkelstein are completely different regions of spacetime? You see, this kind of thing these conformal diagrams make clear. Let me explain that a little better more physically. Where r equals? Oh, this point. You see, it's one of these things. It looks like it's a point, but it's infinity in space. It is both. You should think of it this way. Suppose you go towards the event horizon, and just before you reach the event horizon, you shine your torch outwards. So it's the last light ray that can make it to infinity, makes it at this point. If you did it a millisecond later, you would hit the singularity. Okay? So for causal purposes, r equals infinity on Scri plus and the singularity touch each other. Because for causal purposes, you change a little bit. Something that hits that hits this. So they touch each other in that causal sense. But it's only in a causal sense that they say point. Okay? They touch each other. Okay.
In this diagram, so what do the horizontal and vertical directions represent?
Horizontal and vertical directions. So if you're going this way, you're moving in some space-like direction. You're going this way, you're moving in some time-like direction. Nothing more. Okay?
No, but still, r equals 0 is given by a horizontal line, which...
Well, let's check. R is equal to 0. No, you see, R is equal to 0. Yeah, R is equal to 0 is given by a horizontal line. That is a very specific thing because we can check in terms of these UV lines what the angle is. Give me 2 minutes for that. Okay. You could also, of course, in this plane, compute you know, so let's see, what do lines of constant r look like? You could ask that question. Okay, so clearly if r is very large, you're going to the edge of this diagram. Okay, so very large r goes like this. Other lines of constant r will come like this, r is equal to 2m is like this. Then r less than 2m breaks up. R is beta by 2. One thing is like this, and another thing is like this. Okay? And then when you go towards 0, it just flattens out. That's roughly how lines of constant r evolve in this diagram.
Should not be interpreted, the horizontal and vertical directions should not be interpreted as being fixed r.
No. 45 degrees has great meaning here, but nothing else. Nothing else. Horizontal just means space-like. R and T is not distinguished here. Okay.
Capital T is not the actual small r and small t. So
Which capital R and capital T?
this coordinate is in capital R and capital
Now this coordinate, is going to be in some different thing, because it's only here that it was like flat space. We haven't yet worked out carefully what coordinates this will be. But doesn't matter. Light rays will move like this in the diagram. Yeah, there will be some capital R and some capital T in terms of which it is this, which is very different from anything. Okay,
I am saying that if we do the consecutive, the transformations what we are doing,
Yes.
and then if we want to identify the small r is equal to 0, and maybe we can get this line.
Yeah, we will. You can do that. Once you know what your coordinates are, you can figure out everything unambiguously. Okay? But we have to Get there. Okay. Now, this leaves one more unsatisfactory thing. You see, it looks like space-time ends here and here. Okay? But if you calculate, you compute the curvatures as you approach this way from ingoing Eddington-Finkelstein, or here as you approach from outgoing Eddington-Finkelstein, nothing funny is happening. So it doesn't look like space-time should really end here. And as I told you in the last class, if you just complete this diagram to the maximal amount it will go, you get two additional asymptotic regions, an additional so this point just is called scry plus and scry minus. Future light, the future place where future light rays come. You get a scry plus prime and a scry minus prime. You may want to switch those around. Anyway, you get additional asymptote. Okay, I want to now help you understand how you can more mathematically say this. Say this, and in particular show you a coordinate system that will allow you to see all of the space-time, not just this, all this. This coordinate system is called the Kruskal coordinate system. Okay, so in the remaining, I'm not sure we'll be able to understand the Penrose diagram completely this class, but in the remaining 10 minutes or so, sorry for keeping you so late, we'll at least understand the coordinate system that allows you to analytically continue for this in the full region of space-time. Okay, so the first step we do in writing down this coordinate system, okay, is to do something similar to what we did in flat space to understand the Penrose diagram. That is, we move to u and v coordinates. Last time we moved to v and r or u and r. Very useful things to do. Now we're going to try to do better. We're going to move to u and v coordinates. Okay. So what's our metric? Our metric is ds squared is equal to, now let's see. So firstly, we have to figure out this part and we have to figure out this part. Now, this part is going to be what? There's going to be du dv with a minus sign. Let's check this statement. Okay? Let's take du and dv and compute. Okay? So just like in flat space, this is it will have this plus this times this minus this. So we use a plus b into a minus b is a square minus b square. So we'll get dt squared into this. Oh, sorry. So overall, yeah. 1 minus beta by r, not whole square. And I will need a minus sign, right. So I get 1 minus beta by r into dt squared with a minus sign, so that part works out right. What about here? Here I have to take dv, so that's dr divided by 1 minus beta by r. So here I'll get 1 minus beta by r into dr by 1 minus beta by r, the whole thing squared. So one of the 1 minus beta by r cancels, and we get dr squared by 1 minus beta by r squared. Clear? Plus r square d omega 2 square. Now, exactly as you'd said when we were looking at flat space, what is this r doing here? R is not one of our coordinates. So r should be thought of as the solution to the equation exactly. V minus u by 2 is equal to r plus beta log r minus beta by beta. This equation implicitly defines what r is. You have to solve this equation and substitute r is equal to some function of u and v into that metric. Then we've got a complete metric. Now it's an unpleasant equation to solve. We're not going to do it. Just imagine you've done it. This equation defines r. Okay. Now we've taken all this trouble, but actually at this point it seems like we've done worse than Eddington-Finkelstein coordinates. Why? It's because at r is equal to beta, this coordinate system continues to degenerate. It continues to degenerate because the metric, instead of having rank 4, at this point has rank 2. Because there's just got there's no du, dr, dv piece at all. So it's purely the metric of a 2-sphere. So 2-dimensional metric, not a 4-dimensional. Okay? So sorry, instead of having rank 3 at a fixed R surface, we should have had rank 3. Okay? So or if you just take the whole space-time metric at R equals, this should have been rank 4, but it's rank 2. So either any way of looking at it, it degenerates. So this is not good. So now we take the other Q from what we did in space-time. We'll try to define u and v as functions of u as a function of u, capital U as a function of u, capital V as a function of v. At the moment, we're not interested in conformal issues. We're interested in something much more pressing. We want a coordinate system in which this unpleasant feature that this thing goes to 0 is removed. Okay? Now, this does the job. Suppose you define u is equal to, I'll have to fool around till I get it right, e to the power, what was it? Plus minus u by 4m2 by 2 beta probably. And v, I'm going to try and then we'll get it right. V is equal to e to the power minus v by 2 beta. Might have got the numbers wrong, the signs wrong, and we'll fix it. Okay? Let's roll with this and see what capital du, capital dv becomes. Du dv is equal to e to the power u minus v over 2 beta into minus du dv and then by 2 beta. By 2 beta, the whole thing is square minus. Now, what was the point of this? You see, the real metric had a 1 minus beta by r, so 0. If this coordinate at r is equal to beta, near r equals beta, could develop that same 0, then we've got rid of that 0 by an appropriate coordinate transformation. Because that 0, which looks so unpleasant here, would not be there in this coordinate. Okay? But we're in pretty good business because a 0 is equal to e to the power log. And our u's and v's have logs. So look at u minus v, and so I've got it wrong. This was u, right? So I needed. Okay, so that will be v minus u. Look at v minus u. Okay, it has something that's regular times 2 beta times log r minus beta. Is this clear? So this e to the power v minus u divided by 2 beta will be e to the power, near r equals beta, will be e to the power log r minus beta. which will be a factor of r minus beta. So in this coordinate system, this unpleasant thing here goes away. So if I make this definition, this little algebra here tells us that in the capital U, capital V coordinates, we will no longer have our metric degenerating on the horizon. Now, what is the advantage of this coordinate system over the Eddington-Finkelstein coordinate system? The point of the Eddington-Finkelstein coordinates is that they made a choice. They chose either ingoing light rays or outgoing light rays. They didn't deal with it very democratically. That's why they cover only half of the Penrose diagram. They cover the half that ingoing light rays could see or that outgoing light rays could see. But here what we've done is to be completely democratic. Okay? So there is if we can go through here, we'll also go through here. And it will turn out that these coordinates will also go through here. Okay? So I'll complete this discussion in the next class. What we will have to do now, okay? Okay, let's quickly do one or two last bits. So what we have to do is use this coordinate system to rewrite this metric. Okay? To rewrite this metric in terms of du and dv. Okay? So, okay, fine. Let me leave it as a little exercise. Will one of you, can I get a volunteer to do this next time for me? So, someone other than the two who volunteered. You. Okay? What the exercise is to rewrite the metric in terms of capital U and capital V, and then show that this metric is smooth in this region of the Penrose diagram, this region of the Penrose diagram, and that you can exit here as well. Okay? So you'll tell us about it at the beginning of next class, and then I'll tell you a little bit about the compoundal compactification, how you can see this structure more clearly, and then we'll move on to other things. Okay, good. Our discussion of the first pass at black hole physics is almost at an end. Okay? Sometime in the middle of the next class, we can start talking about maybe gravitational waves. So what do we want to talk about? We want to talk about black hole physics, we want to talk about gravitational waves, and we want to talk about cosmology. These are all bread and butter things. And then we'll try to have some more fun. So we can do that in the next month, I think, the gravitational waves and cosmology, and then we can try to have some more fun.